Today's video lecture is on ionic bonding. We're going to start here in chapters 8 and 9 talking about the basics of bonding theory and what goes on with it. Today we're going to focus on ionic bonding. First of all, overview of bonding itself. There are three types that we'll discuss. There's metallic bonding, where electrons are mobile and they can move between atoms. They're delocalized. It means they explain the reason why we have conductors of heat and electricity, why there's malleability and ductility of metals. We've got ionic bonding, which happens between two oppositely charged ions. We have somebody that loses an electron to become positive, typically metals. We have nonmetals that typically gain electrons that become negative. So those opposite charges are held together. Finally, the last type of bonding is covalent bonding, where electron pairs are shared between two different nonmetals. For example of water here at the bottom. So when we think about Lewis symbols, you've got this figure in your book on 8.1. You guys have done Lewis dot diagrams before. If you think about Lewis dot diagrams, they show you the number of valence electrons around the atomic symbol. It's an easy way to see them. If you notice that everybody in group 1A, they're going to end up with one valence electron, so there's only one dot placed to the side of the lithium. If you look at beryllium there in the figure, you've got two dots on the beryllium because it has two valence, 2s2. Boron's family has 3, carbon has 4 dots. Notice they're placing them equally around the carbon. Nitrogen 5 dots, and so forth. Everyone's trying to get 8 valence electrons, which is called the octet rule. Some elements would achieve a duet, where they would be like helium's noble gas configuration. And that's primarily the elements in the second period, or that second energy level. They would rather obtain the duet than the octet, especially on the left, talking about boron, beryllium, and lithium. Once you get past boron, you get nitrogen, oxygen, and fluorine. They'd rather gain electrons to be like neon. So you need to be able to look at the periodic table and identify the number of valence electrons and place them on there with dots, or this Lewis symbol or Lewis structure they're called. Ionic bonding. When we think about ionic bonding, the ionization energy for sodium is really low. It's only 496 kilojoules per mole. That means that sodium would really like to lose that one valence electron. Energetically, it's easy. It doesn't take much energy to pull that electron away. If we look at chlorine, chlorine has a really negative electron affinity, which means that it would really like to gain an electron. That means it's a stable thing for it to grab another electron. Well, if you think about how this works, if you think about the enthalpies of formation, we know sodium chloride is really exothermic. But when you put these numbers together, it doesn't equal exothermic. It's kind of bizarre. This picture in your book shows this process where you put sodium metal into chlorine gas. I'd really encourage you to go on to Mastering Chemistry and watch a video in the animations and activities that shows the formation of sodium chloride, and you see how exothermic it really is. We know it's got to be really high, but why? Well, this shows what's happening in that process. There's got to be another piece to this puzzle. Sodium, notice, has the one valence electron. Chlorine needs another valence electron, so an electron is transferred over to the chlorine. As soon as sodium loses an electron, it becomes positive. Notice the chlorine on the right-hand side becomes negative with 8 valence electrons obtaining an octet. Sodium gets an octet because now it's isoelectric with neon. It has 8 valence electrons. So these positive and negative charges, they link together. This is what an ionic bond is because of opposite charges. So how does this really work? What's going on with all of this? Well, there's got to be another piece to the puzzle. If you think about, if we just considered the ionization and the electron affinity, when sodium goes through its ionization, and I'll just write that as an ionization here. I mean, it's really low. It's 496 kilojoules per mole. Chlorine, we'll do electron affinity. Its electron affinity is really exothermic, which makes sense because it really wants to gain an electron. And when you put those two numbers together and you sum them together for the enthalpy of formation, you get positive 147 kilojoules per mole. Well, that doesn't make sense because we just saw in the picture And we saw energetically that this is really exothermic. It gets really hot. So why in the world does the enthalpy of formation not give us an exothermic reaction? So there's got to be something else to this. This value that I just showed you is only true when the ions are infinitely far from each other. There's got to be something else to it. And this is where lattice energy comes in at. Lattice energy is the energy needed or required to separate a solid, an ionic solid, into its gaseous component ions. And this goes with an inverse square law called Coulomb's law. You may have seen this in physics. The Q's represent the charges, and D represents distance, and K is a constant that goes along with lattice energy. What I showed you earlier in the enthalpies of formation, that's only true if the ions are infinitely far apart. This takes in consideration not only their charges, but also the distance that they have between them. Let me talk about this a little bit. So as we look at this lattice energy, a couple things about lattice energy, and just kind of the relationships here I think are the most important. The constant's not really a big value for us. I don't know if you have to really think about memorizing it, but just knowing the relationships are important. I'll summarize it here. As Q, and again those are charges, as Q goes up, and I'll just call it LE for lattice energy goes up. So if I had a charge like sodium, Na, with a +1 charge versus calcium with a 2+ charge, the calcium you would anticipate to have more lattice energy because it has a bigger charge, for sure. So its charge goes up. So the bigger the charge is, we see the lattice energy go way up. So it is a function of charge. The other part, as distance decreases or goes down, the lattice energy goes up. The closer we pack those ions together, the higher that lattice energy becomes. Let's think about that in terms of our ionic size. If we take an element, for example, let's take NaCl as an ionic solid. Sodium we know is kind of towards the top of the periodic table versus, say, cesium chloride, and trying to predict the lattice energy. We would anticipate this to have a higher lattice energy, sodium chloride, than cesium chloride. I'll make my chloride better here. Because sodium has a smaller radius. So those electrons are really, really close to that sodium. Whereas cesium, we're talking the 6th energy level, principal quantum energy level, it's really big. So we would anticipate that sodium itself would be much closer, much smaller distance, because its radius is so much smaller compared to cesium. So there's really two things at play here in the diagram. If you go back to the original equation, the bigger the charge is, the bigger the lattice energy. And then as you get the ions closer together with lower distance, that also makes the lattice energy goes up. When we put this together into the equation, this makes sense with sodium chloride. So again, this summarizes it. It increases with charge, but it increases with decreasing size. So you notice at the top you got lithium fluoride, very small radius, very small separation, huge lattice energy. You go down here to the bottom with cesium chloride, very small lattice energy, smaller lattice energy, 657, because again there's a bigger radius. Go over here and compare this lithium fluoride, compare that to magnesium chloride. Magnesium chloride has a bigger lattice energy because magnesium has a 2+ charge. You look at sodium chloride, which is in the same period as magnesium, 788 versus 2,326. So again, the charge has a huge effect on this in terms of lattice energy. So when we write these out, I'm not going to really go over the Born-Haber process with you. I don't think that's a critical part of this. I'm not going to go over that too much in your book, but I do want to talk about how this value actually goes in with the lattice energy and how we come up with these numbers. So here's how lattice energy works. It's calculated by taking the ionic solid, and we'll take sodium chloride for example, and the energy that it takes to break it into, by definition, into its gaseous ions. Now this value has an enthalpy of delta H of 788 kilojoules per mole. Now that's still endothermic. So how in the world is this exothermic? Well, realize that this is the solid going into the ions. Lattice energy is about the energy needed for formation. So according to our rules of thermodynamics and thinking about Hess's law, if you reverse this reaction to take a sodium ion with a chloride ion to make the solid, like NaCl, the value of delta H is the same numerically but opposite in sign. So this is negative 788 kilojoules per mole. Now we get our big exothermic. Lattice energy is the energy that happens when we take two ions and then we form the solid. And we get that from the formation. And again, this takes in consideration the size of the sodium being small, takes in consideration the distances and the overall charge between sodium. So this is how we get this reaction to end up being exothermic. As you start working through the problems tonight, you're going to have to be dealing with the number of ions that you've got, looking at the effect of lattice energy on charge, and talking about how we can rank those using that figure in your book. Thanks.